Hi, welcome everybody. This is Nalini Elkins with Industry Network Technology Council. And today we're going to talk about a fascinating topic, which is IPv6 and 5G. I know that I've had a lot of questions about how this is going to work. There's a lot of misconceptions. And so I am hoping that Uma will help us get ourselves straight in this area. So looking very forward to this. I'm sure most of you have been to many of our presentations, but for the new folks, this is a collaborative effort between the India Internet Engineering Society and Industry Network Technology Council, both a nonprofit organization with the aim of increasing participation in standards bodies in India and helping enterprises globally to participate, as of course the internet affects all of us, including business. We have had collaborations with ARIN and APNIC to provide training, security, and V6 deployment. And we did a whole lot last year to set the stage. And we are continuing this year with some more advanced topics. Just a few things about me, which I think many of you have heard. But let's talk about Uma. Uma works currently with Intel on 5G topics. He has a vast wealth of experience at various technology companies, as well as working in many areas of the standards world. And so without any further ado, I'm going to go ahead and turn it over to Uma, and he's going to discuss the evolving 5G deployments and explain some of these new terminologies to us too. There's new acronyms we've got to get to know. And as always, INTC and IASOC are nonprofit organizations. We do not represent any specific vendor, and we certainly do not recommend any specific vendor. We are doing these presentations for your educational purposes. Okay, so let me make Uma the presenter, and we can hear what we've come here to listen to. Okay, Uma, go ahead. And as always, this webinar is being recorded. So Uma, you're up.
Oh, can you see my screen?
Yes.
Thank you, Nalini, for the great introduction. Thank you so much for setting the stage and the background. Hello, everyone. My name is Uma Chunduri. Today, I'm going to talk about IPv6 and evolving 5G deployments. A quick introduction about me. Thank you, Nalini, for the introduction, but just in my words, I've been in the industry for almost 20 years. Currently working as a cloud native edge architect in NPG group in Intel. I joined a few months ago as a 5G network architect at NGS, Next Generation Standards Group. Previously, 4.5 years, I worked at Huawei FutureVS as a Future Network CTO office. As a distinguished engineer, worked on many technologies, and especially on the deterministic network services, 5G beyond 5G network transport, network strategy, technology research and standardization. Before that, almost 8 years, I was a principal systems engineer at Ericsson USA, and worked on a couple of other companies too, in Kineto Wireless, Freescale, and Arisent. I have participated in a couple of STOs, like Nalini mentioned, co-authored many work items in my career. So hope this will be interesting for you, and you'll get something out of this. Thank you. So my presentation I will put into 4 segments: IPv6 and well-known facts, 5G deployments, and strengths and challenges. I'll be happy to take questions in between. But if you can hold on to the towards the end of the presentation, that's good. Continuity purposes, if you take it during the presentation, feel free. Okay, let's get started. We'll go to the first segment, which is well known to a lot of the experts here. But just to set the stage and put the context, I put these 1 or 2 slides for this. This is a quick recap. These are some of the milestones I picked up on IPv6 over the period of time, last 20, 22 years, 25 years. Many major milestones happened for IPv6 deployment, right from in 90s, early 90s discussions about IPv4 exhaustion and a lot of buffs for eventually creating the 6-bone working group creation in 1996 to RFC 2460 IETF draft standard in 1998, the first significant milestone with respect to standards for IPv6 draft standards. And over a period of time, a lot of deployment started taking off. Especially the significant one is 2007 to 2011 period. Couple of things happened. All major operating systems like desktop operating system like Windows, Linux servers, and also mobile operating system iOS, Android has taken IPv6 seriously. They have implemented it, they have deployed it. So that's a significant milestone. And the another one is 2012 World IPv6 launch day. A lot of internet global routing started, and a couple of operators started deploying it from 2012. It's a major milestone. And the significant increase I see that happened is increased OTT adoption from 2003 onwards, 2013 onwards, like cloud providers and OTT providers. So there are some benefits. They saw that with IPv6, they started take this seriously, and from dual stack to even IPv6 only. So then 2017. We know that RFC 8200 has been published as an IETF standard, standard 86. It's only 95 out of 9,100 RFCs IETF has ever published. So it's a big landmark. There are significant advantages that shows the maturity of the IPv6 technology, but also it has, it's a double-edged sword because the bar is so higher now with any additions, enhancements to the IPv6, which is in the standard, right? So yes, so then in 2020, and IPv6 and 5G together has been also started in 2020. So just a word about that OTT deployments in cloud and OTT. We know that content providers like IPv6 adoption mostly because of the performance reasons, right? So we remember, if you might remember, in 2015, LinkedIn infrastructure director giving great presentations about how that company is being transformed with IPv6 and what are the gains they're seeing with respect to loading, adoption, and experience with IPv6, right? So there's a lot of middle boxes are avoided, and you have latency benefits, low latency, a few milliseconds, but it's a big deal. And you have less TCP drops, DNS resolution improvement, so many good things with IPv6. So the same thing happened in Google, Alibaba, Facebook, so many other companies that period. And a lot of companies are also moving from dual stack to IPv6 only. Now coming back to our topic, cellular networks. Yes, it's not new, IPv6 for cellular world. It started in 4G LTE deployments in 2008, 2009 release 8 time. So release 8 IPv6 and RS are documented in 3GPP standards, and there's some couple of usage mandates for UEs, and also to the infrastructure side. This from 3G to 4G, that's a big leap in cellular world because it's all IP network. So they wanted to latch onto the future, that is IPv6. So major US cellular carriers support IPv6 today in their networks. Many IPv6 only networks also started being started in cellular world in recently too, right? So now the question is, in 5G, what is the story about 5G, right? So 4G, we know that this has been happening. We are all being users to LTE devices where IPv6 is used, layers and all the stuff. So what is the 5G? That's what we're going to see that. One more slide on IPv6 deployment. If you see this slide, this will show us that this is the World IPv6 Launch Measurement Organization slide. That's the information. So you can see Reliance top of the list, Reliance Jio 90.94 IPv6 deployment in their network. We'll see what we're talking about 90.94. Where is it? This is in service layer, underlay, overlay. We'll see about that a little bit. So, but it's a significant percentage of deployment of IPv6 usage in their networks. We know Comcast is a big supporter of IPv6. They have started this journey long back, and still it's 71%. Couple of other carriers, these are fixed side, Charter Communications and a couple of other folks, and in mobile, AT&T, T-Mobile, Verizon, all folks are doing IPv6 at certain different percentage levels though. And in Europe, you can see Dutch Telecom, Orange, a couple of other carriers, the percentages here. So that's a great to see IPv6 is being adopted in a lot of operators, both in cellular and fixed world. So overall, where we are with IPv6 is Google. It's a great measurements, great information from IPv6 on the Google side. So they closely track it. They want to see this is getting deployed more widely, so they get all the benefits of their network and their services to the end users and to their customers. Where we are at November, 33.63%, 69% overall. It's a growth. If you see the last year, there's definitely growth in the overall IPv6 adoption in the worldwide, and they also nicely represented in the world where this is being deployed. You can see that Reliance, so that's 90%. You can see that dark green in India, and North America dark green, and there are other couple of places where it's being deployed trials, and some part of the network is transformed to IPv6. So that is represented here. So it's increasing overall, but at the end of the day, it's all about applications and enterprise adoption that really matters for the maximal benefits of IPv6. So regardless, you have an IPv6 address into your end device, it has to be at the applications and enterprises that has to adapt to get the maximum benefits of this technology. Now let's quickly go to the 5G deployment status, to the second segment. Let's back to the 5G world, where it is with respect to 5G deployments. It's not new anymore. It's 2 years since deployment started. So we can see 176 commercial 5G networks already launched by August of 2021. 461 operators in 137 countries, territories invested in 5G. You can see the dark blue, 5G deployed in the network, services launched already, North America, and some parts of South America, China, and Australia, Europe, a lot of parts of Europe already. And in the purple, 5G deployed in the network. It's a pre-commercial. It's pre-commercial, not launched fully. It's a planning stages. A lot of countries in planning stages. For example, in India and in Greenland here. So yeah, and some countries are still deploying and planning. So all the rest of the world, in various parts of the world, in various different stages, 5G is being deployed. And one staggering information is there are around total 938 announced 5G devices so far. This is from GSA. They track all the information with respect to 5G statistics. So 938 announced 5G devices. And that's an increase from 350 to 580 in 6 months, last 6 months. A lot of activity happened this year. And overall 600 commercial available 5G devices today, the UEs we're talking about here. That is the handheld devices or anything like that, so something like that. So we'll get to that. So with respect to connections, there are 234 million connections in 2020. It just doubled in 2021, 538 million. It's going to be 1.8 billion in 2025. That's the projection according to GSA, GSMA. 5G is not about handsets. We know that. Only 50.5 of the handsets of the UEs, you can see that out of 900, around 400 are around the handsets. The non-handset devices are going to increase further, that is MIoT adoption by 2025, so that the total overall percentage will be reduced, obviously. But what is the silicon system providers like Intel? We have we are interested. We are investing in almost 8 years, 9 years. There's technology leadership with respect to 3GPP standards, product, services to all operators, and a lot of operators in across the world. Our goal is to democratizing access for many 5G deployment scenarios. Disaggregation and virtualization is the key. It just simply can't, in the old model, you cannot deploy this 5G services because it's so much elasticity there. You have so virtualization and disaggregation is the key to scale the network, to offer the new services close to some places, and and scale out architecture. So these two technologies are very clear, very important. So operators recognize that. Cloud native, from virtualization to cloud native, the many focus, it's RAN and core networks. So it gives auto scaling, fault tolerance, and centralized operations, security and latency. So these are some of the key things what silicon providers are looking like Intel, and to help with the transition to the 5G world. And there are a lot of work already started happening on beyond 5G. The key use cases just network AR/VR, higher uplink speed, and artificial intelligence and machine learning in the RAN and core. We'll see what is RAN and core in a bit. I just want to put this here. When you put the 5G well-known triangle here, I just want to see overlap where 5G is happening, in which triangle, which corners 5G is happening as we speak. So right now, it's all enhanced mobile broadband. All these 230 million, 538 million connections were mostly about enhanced mobile broadband. That is, you have higher speeds. Basically, you have, because 5G NR provides in the radio level, you have higher speed, so you have a better experience overall, and fixed wireless deployments are happening. So this is the predominant use cases of the 5G deployment today. But there are other 5G promises which are being touted for last 5-6 years, right? So that is MIoT, massive mission communications. That is, it's not about you, it's all smart city devices and smart home devices, all these different kinds of IoT devices hooked onto 5G, which will bring benefits to the entire industries and societies, right? So this is MIoT, and there is other corner which is extremely stringent SLA-based communication based requirements. Ultimately, V2X services, a lot of devices, all self-driving cars. So this has a different kind of set of requirements for with respect to communication. Does this connectivity layer have any role in to play in future for these two corners, right? So will this be in the network? Will this be MPLS v2, or IPv6 will catch on more rapidly? We'll see. Okay. So where exactly IPv6 is being deployed? Let's look at the architecture. So this is the 5G architecture. You can see that's UE. UE is user equipment. It's a handset, and so RAN is the radio access network where your radio mats and the towers, all the stuff is there, and you have the equipment RAN, and you have the unlike 4G LTE, you have a core network is completely transformed, and the 3GPP standards is release 15. Architecturally also it provides that cloud native capabilities. Basically, they recognize that it has to scale, it has to support these many number of devices, these many number of connections, this speed and different kind of SLAs. So they recognize that, and they architecturally they separated the control plane and user plane, that is the data plane. So so this can scale in differently, scale out differently, scale out independently based on the deployment, right? So this is the control plane which is being shown here. And with respect to IPv6 service layer, you have IPv6 addressed to UE. Applications are using IPv6, that is there, IPv6 here. And in the data plane, these are the interfaces, N3 and 6 and 9 interfaces. It has two components. One is underlay network and overlay network. Both can use IPv6, in some cases only one. And in the control plane, all this control plane, instead of fixed function boxes, it's getting virtualized from 2016 itself in the LTE days. Now it's getting cloud native. So this control plane can be run in the clouds or in the edge clouds. Makes sense to have IP6 based control plane. A lot of people are looking into IPv6 because the service mesh and the granular security benefits it can offer service meshes with IPv6, right? So you can provide security services more granularly with IPv6. So there's a lot of work that's happening in this area. to bring the service mesh and auto scalability with a lot of security features in it with IPv6. Now, let's little bit expand this from this block, from this 3GPP specification document, what exactly how it looks. This is the first level of expansion. If you see that you have UEs and RANs, there's a 3 components, radio access network and the transport network with all these routers and switches, and you have a core network, either it's fixed function boxes or virtualized core network, and eventually there's a lot of compute, intelligent compute, ubiquitous computing, because a lot of computing needs for low latency purposes and for the end user experience purposes, the compute has to be closer to the network. It's there in the CDN's time in LTE, but even rapidly that compute is getting closer, even closer in the aggregation network and pre-aggregation, even far edges near to the base stations itself, some cases, right? So for V2X scenarios, so you have the ubiquitous computing, including in the cloud and including in the edges. So with respect to IPv6, from the UE side, the 3GPP supports both IPv4, V6, and L2 unstructured, all kind of user sessions. Their standard overlay protocol is GTP. But in UEs, predominantly it's IPv6. As we see in the earlier charts, IPv6 is mostly dual stacks and very few, some cases IPv6, but mostly dual stacks, IPv4 and IPv6. But unfortunately, the question is what is in the network? Whether IPv6 is fully catching up in the network or not is a question. Unfortunately, NATs are still there in the IPv6, even in the core network. Even though DHCP-v6 gives the UPIP address, eventually those are not GUS in some cases. They want to keep the control at the core network when the packet emits out and comes in. So there's NATing happens with the addresses. So this is kind of intrusion detection antivirus kind of first level firewall that the NATing function. Yes, IPv6 has stateful packet filtering, but still operators seeking to use NATs. This is yeah, this is kind of the reality right there. And you can see performance perspective, similar benefits of using IPv6 in the cellular networks as in the other networks. Like we see in the OTT cloud, the single most important and benefit they saw and moving to IPv6 only is the performance. You get rid of a lot of middle boxes in the network. You get rid of various NAT and other functional devices in the network which are legacy and which creates all kinds of latencies into the network. That's what you can get rid of through IPv6. Supposedly that's what the OTT was doing. The same benefits you have in the cellular networks, end-to-end latency reduction in the DNS, hard DNS, and TCP, less TCP drops, not fully specific to IPv6, but IPv6 gives some advantage there, right? So, and obviously at the end of the day, eventually when MIoT catches up from EMBB to MIoT 5G deployments, you will have situations where highly dense UEs in the concentrated. So you will end up, operators end up moving to IPv6. They have to move it because they you cannot provide the addressing to all the devices, right? So, but a lot of operators are preparing, but that will be more faster maybe coming years. So in the applications, local compute, in the local compute cluster or cloud compute cluster IPv6 for the applications, and the end user IPv6, we know that, but the network we'll see a little bit more now. So 5G topic is incomplete without touching the slicing and shared networks. For the economies of scale, the network has to be shared and it has to serve all kind of traffics, including EMBB, URLLC to IoT devices, which are quite different in nature with respect to the traffic profiles and the nature of the traffic and the requirements from the network, end-to-end network, to give the what you call end user experience, and are the vertical segment that's going to be served with these networks, right? So that's where the slicing comes into picture. So so what's the IPv6 role? I will touch base on this. The key point is why IPv6? This is a question here. This is unsolved question, kind of, people are working on it, people actively working in SDOs. So RAN and core, this is governed by 3GPP RAN and core network. These are virtual instances, physical or virtual instances for different slices. This is clearly documented for end-to-end benefits. Transport has to be also in sync with RAN and core. That's where IETF is working a lot of working groups, and from T's to 6-man, and a lot of routing area work is happening in the transport slicing area. So there are some of the features like QoS, predictable latency, isolation, SLA-based delivery, traffic engineering, all are the key features which are relevant to connectivity layer. So let's look at the network, right? The typical network, how it looks like in operator networks, USB network, communication service providers, which are serving not only MBB with the slicing, with all kind of end devices, and with all kinds of V2X scenarios where mobility is involved. So your RAN is virtualized and disaggregated as we talked. So your LAN is split into two, distributed unit and centralized unit. So you can pool in the cloud RAN, you can pool all the computing functionality at the central place, and you can put the TU close to the base station, so you can aggregate the traffic here and you can virtualize the traffic, right? So this is where the disaggregation is happening, and in between there are transport networks between TU and CU. The splits are governed by 3GPP. What kind of split is where applicable, which country? There's a lot of dependencies there, but it's not relevant to completely IPv6 here, but there's a lot of work that's happening here, virtualization and disaggregation. But the key point here, this is the traditional transport network, and UPF is also now data plane. UPF is also getting disaggregated. It's not that single P gateway at the central location. It can be, UPF can be at the aggregate nodes, so you can have local computes here for the latency application. You terminate the connection here locally, and you can get the low latency benefits, right? So that's where this architecture. So the key point here is network is completely disaggregated, right? So then you have the complexity. If you put MPLS everywhere, there's a lot of complexity here. So from the protocol stack point, some people asked, what are the protocol stacks here involved here? So we have the traditional IP, TCP, and application layer. These are the radio layers, PDCP, RLC, MAC are the radio functionalities, and 3GPP layers, lower layers. So in between, this is what, when the UE emits the packet, this is the packet looks like stack. And when it gets to the DU, that's where the GTP overlays are used, TCP encapsulation, and this is essentially UDP encapsulation with the GTP protocol, conveying the different kinds of information from the radio base station to the core network with the GTP overlay. And in the underlay network, you have VPNs, VPN labels, MPLS, traditional MPLS, or RSVPT or segment routing MPLS, and some cases now SRv6, IPv6 is being deployed in the networks, right? So this is where the first starting point where IPv6 is started. We know that this IP is IPv6 and the end user IP is IPv6 application, but in the core network, in the operator core network and the transport network, IPv6 is started. But frankly, the requirements from the connectivity layer are for 5G is different than LTE, right? So because LTE you have always about bandwidth, higher bandwidth, but here the network is massively disaggregated and different kinds of traffic are being served in the same network. So depending on the type of the vertical, 5G vertical we're talking about, the packet delay budget, these are the end-to-end delay budgets. I gave some examples here, key SLAs, and the packet loss and the service type. Based on the service type, these need to be served. For example, if you see a discrete automation, the end-to-end packet budget is 10 milliseconds and 10 power minus 4 packet loss. There's no way you can put this in the centralized place in the UPF and terminate the connection here. The discrete automation has to happen in the local, in the factory floors. So it will be close to this, your network will be close to here, and your termination point is close to here to serve the 10 milliseconds. For example, in some cases you have 50 milliseconds real-time gaming and all. So that's where you have edge deployments in a different purpose, like different places that can be put. It could be close to P gateways or UPFs here on the pre-aggregation networks. But the key point is you have the delay budget, so you have a network segment delay budget. So this connectivity layer has to play a role to help this connectivity SLAs. Though RAN and core network is governed by 3GPP, the binding thing, which is the connectivity layer, is layer 3. So that's the where IPv6 can potentially play a role. Now there's a huge world, other world that is happening apart from the communication service provider networks that we have seen. That is private 5G, because because of the complexities and because of the private, basically they want to have separate spectrum, separate network for a dedicated functionality. It's more stringent LS, like a SLAs, for example, smart factory kind of scenarios, industry 4.0, which has uh, the stringent, you can think of SLAs, because there is a, it's not for communication anymore. This is for the connectivity. This connectivity is for much higher purposes, right? So this is for industrial automation. So your SLAs are more stringent. That's where private 5G edge deployments are happening. So Intel has many edge offerings, which is this is like many other companies. A lot of industrial offerings are there, which is completely with the private spectrum and complete end-to-end network governed by one vendor. So there also there's a lot of connectivity. Are they thinking about IPv6? Not much right now, because they have many other challenges than the IPv6 right now in those deployments, private 5G deployments. However, so these are the characteristics which connectivity layer can offer. That is deterministic behavior, like IETF.NET is working on so many years. Put these kind of characteristics in the network, which is more control, you have more control, but that doesn't mean that they solved all the problems. But these are the requirements: deterministic behavior, end-to-end QoS, and slice identifier in the packet. You have to run many situations, timing synchronization from the network, core network, to all the way to the base stations, to the UEs. And that's where your connectivity layer has to carry some timing information in some cases. And you also have to have the connectivity layer has to provide the SLA-based delivery in the transport networks. So all these players, connectivity layer features in these areas can further change the rate of IPv6 adoption. That's the future. Next 5 to 6 years, we'll see that as in more and more use cases are happening, then the connectivity layer also evolve. Intel is committed, has been working on many years, including hardware, software, middleware is IPv6 ready. There's a lot of middleware work that is happening when they go to cloud network, cloud native network. In the core network are RAN, where the various tools are IPv6, so that need to be ready for the end-to-end IPv6 benefits, right? So, but there's a lot of work that has to happen too. So with all this, where does this leave us, IPv6? It's a mixed bag overall. So let's look at there's some of the questions that's asked by the organizers: IPv6 and MOVT scenarios in 5G, where it is now, what is the status, it's happening or not happening. This will be the driving force for IPv6 and 5G. It's kind of yes or no. IoT space is vastly fragmented, from constrained to low power to no constrained devices, right? So 6LoWPAN is getting deployed in constrained environments big time. But the billions of devices to be connected to 5G, a lot of it connected through edge gateways right now. Not all require IPv6. They don't use any IP at all in some cases, unstructured UEs they are, so to speak. So those are constrained devices. But there are other V2X that there's no constraints. They can use IPv6. However, the operators right now, the other priorities, they want to first establish the network. They want to roll out first initial services, EMBB. So until there is a push for complete IPv6 absolutely needed, they are surviving, right? So, but at the end of the day, it will change eventually. And dual stack is being deployed. Now, with respect to IPv6 and 5G deployments, there are great examples, great greenfield. Why they are using that few Asia, the well-known names, it's publicly available information. Rakuten is there, Rakuten is deploying, SoftBank is deploying, and KDDI and a lot of Japanese companies are deploying all IPv6 networks. They recognize that the value of IPv6 because it provides a clean architecture with unified service layer and underlay. We have seen the service layer that is to the UP, and the underlay network is a unified network with complete IPv6. It provides network simplification. The more you disaggregate the network, virtualize the network has to be simplified, and it has to be single one connectivity layer. That's where IPv6 brings both at the end user and in the network. And it's future proof, obviously. At some point you have dense areas where you need to do massive IoT connections, so which are not constrained. So you have to have IPv6 address there. And performance gains, obviously, we have seen this, less unsupported gear, less middle boxes, and it's a definitely huge performance gains. And in brownfield, many networks in North America and Europe and Asia, you can see T-Mobile, DT, Orange, some of our customers, they are transitioning to dual stack, to some cases IPv6 only. And there is a, UIPv6 is there from LTE, but it's increasing. But the key question is whether underlying networks are also being transformed or not, and that is happening as we speak. So I will stop here. If I wait for 1 or 2 minutes, if you have any questions, I can take it now.
Yes, Uma, there's a few questions that have come in. Let me just go ahead and take the time now to ask. So first, this is a clarification question. When you talk about connectivity layer, is that the same as the transport layer?
Yes, that's correct. In the underlying network, that's the transport layer. Yes. Although, wait a minute. The transport network and transport layer is different. Transport layer is your TCP, UDP, your overlays. I'm taking connectivity layer is the layer 3.
IPv6. That's
Correct.
what you mean by.
Correct.
Perfect. Thanks. So layer 3 versus layer 4. Great. Okay. So another question. There's some questions I'll save to the end. So one question where for URLLC use cases where the user plane elements are closer to the device. So IP routing is usually within the prem. So then you're going to have a limited number of devices. So do we really need IPv6 there? Wouldn't IPv4 be sufficient? What are your thoughts?
I think that's a correct observation. Today, the requirements for the URLLC cases where you are on-prem 5G kind of private edge deployment. Right now, there is no clear benefit IPv6 give at this point. However, as I said, if any of these features are there, that is happening, work is happening in various IETF working groups like DetNet, a lot of work is happening in 6-man, the slice identifiers, timing signatures, and IPPM is doing a lot of work. Any of these features can get into the IPv6, then that's where people will come to IPv6, IPv6 not go to them. The IPv6 where people will use IPv6 there. That's what my understanding so far, because these are the features right now. These are the some QoS and slice identifiers are putting into the extension headers in 6-man. DetNet is working on IPv6, all kind of connectivity layers, including MPLS. There's not much work happening in IPv4, right? So MPLS and IPv6. There are some proposals for putting the timing synchronizers, timing information through extension header in the IPv6, or some features like SLA-based data delivery, lossless packet delivery in the connectivity layer. If any features for network visibility in the IPv6, that's where people will come towards IPv6 if these gets matured.
Very, very interesting. We ourselves are working in IPPM on some performance and timing drafts. So there's more questions I'll ask you at the end, but thank you so much.
Yes.
Yeah, let's keep going. Okay, perfect. Thank you, Uma.
Thanks. So finally, there's a few challenges and ongoing work. We know that a lot of people who are working active in IETF, they know that a lot of ongoing work is happening in various working groups, which are relevant to 5G and which are relevant to IPv6. I segmented this into 3 parts in the underlay network, that is in the connectivity layer, basically from your radio base station to the UPF, that is the mobile core network, the packet which is going through the transport network. So there are challenges with IPv6, right? So you have MTU related concerns and strategies. It's there, and if you put a lot of information in the packet, you need to rebase the network with MTU and other strategies around it. 8200, even higher bar for deployment for specialized features. Because it's a standard IETF standard now. The extensions in the framework of IETF RFC 8200 would okay, but if there are some cases where there are gray areas, that's where the contention, a lot of contention, the bar is extremely higher now to change anything in 8200. So that's one challenge, but the work is happening. Extension header, it's a complex architecture, processing lower heads, especially in the legacy networks. You have a low-end nodes. There's a performance penalty. If you have a lot of extension header in the packet, it'll go to the software processing, and all the latency gain in one area will be lost in the network, which is kind of the determinant factor, right? So these are some complexities, but SRv6 is a great example where people deployed SRv6 in the IPv6 only networks. They're seeking end-to-end IPv6 network, but it needs compression. We know that a lot of work is happening there. For example, SRv6 they themselves come up with a solution in the data plane solution like CSED. There are other solutions like SRH and data plane agnostic solution like preferred path routing, which are IPv6. So which takes the route of putting carefully the packet headers, what you put the information, be careful. And let's say you don't want to bloat the packet with a lot of identifiers in the packet, but put the relevant information, the SLA information, the latency constructs, or the packet loss construct. These are the packets you need to put this information into the extension headers, right? So there are inevitable, in some cases, you need to have in the public deployment, CH and ESP will be there. With IPv6, you have for path steering and low latency benefits, segment routing kind of headers will be there. And you have for VPN, different kind of VPN, like VPN plus. You have a destination option, you put VPN label there. So for IPPM, all these features are needed at some point in these networks to get the maximum benefits, but also create complexities with all these features together going into be deployed. So determinism in the IP layer is extremely important in future. Once CMBB is done, deployed, people look for more wide area kind of a network DRVR, like V2X scenarios. That's where you cannot put everything in the on-prem. You need to be in the network, so that you inevitably touch the transport layer, you inevitably touch the connectivity layer, underlay network. So where this lossless delivery and T-enabled fast reroute, granular OAM, IPPM, a lot of work that is happening in IPPM. All these are extremely important. And the DET network, the TEAS working group that is happening, predictable latency constructs, not only in the connector, in the packet headers, also in the network nodes, that has to happen. Also, there's a lot of debate that is happening. Do we need limited domain specific IPv6 extension? There's a lot of debate is happening, but this is an open question. How far, you put some features like, which are in the gray area, but specifically there are many problems in the network layer that can be solved with those features. These are the underlying network scenarios and features, and the network programming is happening. Both SRv6 has taken network programming with the IPv6 address itself. You can program the network, or with the extension headers. Both features are happening, right? So that's great news. Adoption challenges in service layer. Application migration is slower than endpoint addressing, right? Application migration, but it is, I saw somewhere around 80% UEs IPv6 migration, and around 50% applications, right? So it takes time. New applications will be both the dual stack and IPv6 only, but the legacy applications takes time. Enterprise migration is still slower because, again, the legacy. Operational challenges, network management software, and some rich tooling support. There's a lot of tooling that happened over a period of time now, but in the operator network, still the level of tooling for IPv4, IPv6 is vastly different. So these are some of the challenges. But these requirements and features can make a significant difference for IPv6 adoption. This is not for IPv6, this is for 5G too, because these are the things that is needed for 5G, successful 5G deployment beyond EMBB. For example, dense urban areas, you have no way, you need to support a lot of IoT devices, MIoT devices, you eventually address space issues and private. You cannot go for IPv4 and keep NATing there. So you have to use GUAs, you have to use IPv6 with NAT or without NAT, and you have IOM and in-band telemetry. This is extremely important, measurements and network visibility, because if you provide the service SLA-based delivery, you need to commit to the packet delivery for that level of service levels. So you need to measure the network. You need to continuously improve the network performance. And the zero trust security, as we see that infrastructure is happening, infrastructure transformation is happening inside the core network, there with the cloud, from virtualization to cloud native. And a lot of zero trust security work is happening. IPv6 has specific advantages there with the granular security policies to the infrastructure work elements, because to protect this, because the moment it gets virtualized, it has to be more secure, more robust and reliable. And in underlay network, we touch base this. The moment it's slicing, and even for the non-slicing scenarios, traffic engineering is extremely important. Isolation of the traffic. So you need to steer the packet from the source. Source routing, segment routing is extremely important, these features. Capabilities for SLA-based deliveries in the underlay is important. Network programming. Both with IPv6 address or through the extension header. Today we have all the tools, unlike 5-6 years back. You have P4, you can program the underlying device with your ASIC, your silicon, and you can program the network layers, right? The APIs, you can program it through P4. All the tools are there. And if you have a mature protocol, this can be implemented, and the services can be rolled out into the network. And eventually measurements and visibility, as we said, that this is important both in the service layer. When the packet is delivered to the host, there's a lot of cloud native functionality that will happen to eventually pull the packet to the application, right? So you need to make sure that latency is not introduced there, right? So that's where in the overlay, but in the underlay, when the packet is delivered in the transport network, you need to make sure that measurements and network visibility is there. So final thoughts. IPv6 can bring a lot of advantages to the 5G deployment for sure. The three areas I can see is innovation, differentiating features to address 5G L3 network requirements, and IPv6 a huge difference. I touch base some of the features there. Network simplification, as we see, the network is massively disaggregated, virtualized, cloud native. It's not like a fixed function. It has to be scale out architecture, right? So it has to be then simple. The network has to be simple. So it's an end-to-end, one single end-to-end connectivity. It's a great benefit. So if you fragment the network, you have in the RAN, you have layer 2 network, you have IPv4 in some part of the network, IPv6, MPLS in some part of it. It's extremely complex network, right? So it's a single end-to-end connectivity layer 3 will be a great starting point to scale out the network and to build more services into the network. And security, not discuss specifically about how this happens, zero trust networks, but this is advantages. But if you use GUS, they have perceived privacy implications too. So a lot of work is happening. So it's a work in progress from my point of view. I'd be happy to take questions now.
Great. Oh, this is absolutely incredible, Uma. It's such a dense presentation. It's going to take me quite a while to think over all the things that you've said, and we're certainly going to have to start some conversations, offside. But let me ask you some of the questions that have come in, and if anybody would like to speak, go ahead and raise your hand. I see some hands. And when you ask, please just identify yourself by your first name, if you would, because there's, otherwise I have to get, because this is being recorded, I have to get, disclaimers and this, that, and the other thing, and it's a lot of work. So anyway, so let me ask let me start with the beginning. So the IPv6 deployment slides that you showed were very, very good. Do you have any visibility to the IPv6 deployment in China? You did mention Alibaba. So do you have visibility into that?
Yes, we have customers. So I cannot disclose the names, but we have customers in China who are transitioning to IPv6. In my previous employers too, also their network transformation is happening in LTE days. So yes, China is rapidly deploying IPv6. I'm not sure they are building complete IPv6 only networks. Most of the things I've seen is dual stack networks, IPv4 and IPv6, because it's the fact that it's a legacy network. So they're transitioning to IPv6. in a lot of places, yeah, it's mostly dual stack. I haven't seen IPv6 pure IPv6 only network like Japan is doing, like, right? So I haven't seen, maybe that's happening, but I'm not aware of it. Mostly dual stack networks, but a lot of IPv6 adoption there. Yes.
Yeah, I'll have to chase some people down, see if we can find that. So another question. So this has to more do with business adoption. So do you have an idea for, like, the carriers? Certainly we know why Geo is moving, but like T-Mobile has moved to IPv6. Can you talk about their business and technical reasons for doing that? And I know you talked about a lot of the 5G related, but what is your thought on that? And I'm going to let the gentleman who asked that, I'm going to unmute him so he can talk to you himself.
Sure.
Yeah. Mike,
yeah, this is Mike, and Nalini articulated the question very nicely. And let me say first, though, this is an incredible amount of great material you just discovered, and I greatly appreciate it. I think we all do. But that particular question, and I'm an enterprise person, and so I'm coming from that perspective. But you had a slide that said some of the carriers are going for their 5G deployment and using IPv6 as part of their infrastructure, and I'm wondering why. Because if they good business and technical reasons why they were going there, maybe we should have those same reasons as well. So that's the sort of the idea of that question.
Great.
Yeah,
great
and
question.
that's the exact slide. Thank you.
Yeah, great question. Great question. Yeah. So I think as we see this, right, the greenfield networks, if you have a luxury to deploy the network, you see that in some cases in SoftBank in Japan, Rakuten, it's this completely different network architecture they're coming up with, right? So they are taking all the cloud native principles and, all the virtualization, and they want to roll out the services with complete automation, right? So if you have different parts of the network with different technologies, layer 2 in RAN, and some part of the MPLS network in the core, and the basically in the transport aggregation and pre-aggregation layers, when you have to put the edge computer near to the base stations, near to the aggregation network, the network is getting extremely complex. So they recognize that, and in some of the greenfield deployments, they want to use simple connectivity, single connectivity IPv6, and they have used SRv6 service, segment routing, because you need to route the packet, to source route the packet from point A to point B in the network. So SRv6, SRMPLS is there, but that's where they see they want to have a single connectivity layer, right? So, but at the end of the day, this in the network, on the overlay side, anyway, that's IPv6, they want to be future ready, right? So they know that though they're offering EMBB services today, they have to offer soon MIOT services. There's a lot of dense areas. So you have IPv6 addresses there at the overlay service layer anyways. So they want to have a single IPv6 network end to end to reduce the what you call complexity, and also some cases performance, and future proof. All these are the reasons why greenfield IPv6 is happening, end-to-end 5G. Great examples in Japan and in some in Canada.
Okay,
but,
so
yeah.
Well, if I understand that answer, then it sounds like they're going in that direction for a couple of reasons. One you mentioned is to be future proof, and that's good. The other, you talked about they're moving to IPv6 and using segment routing. So I'm assuming they're doing that to enhance performance and hopefully decrease latency.
Yes.
So that would be a good reason too. And I think that was the main reasons that they're moving there, and those are good solid reasons that we should consider as enterprises as well. So thank you for elaborating on that. Appreciate it.
Absolutely, thank you. Great question. Yeah.
Yeah. So sorry to interrupt you guys. I get all excited. But I'm gonna reach out to Uma, and then see, because I would love to get SoftBank or some of these Rakuten or some of these people to talk themselves. And so there's a lot of, I mean, I'd love to get the DetNet people, too, to talk. There is a comment, and so about greenfield networks. Would love to get your comments on that. And what they're saying is that for greenfield network, if you're going from V6 for day one, you can use 3GPP SSC mode 3 with multi-homed IPv6 towards the user equipment and seamless mobility. And so what is your thought on that? Do you agree with that kind of thing?
Yes, SSC mode 3, basically service and session continuity, right? So service and session continuity with IPv6. I won't say IPv6 bring benefit, direct benefit there, but yeah. What I would say, right? SSC 3 mode, particularly not specific to IPv6 as far as I see. Yeah, so basically SSC mode 3 is essentially you have edge computes near to the close to the aggregation and pre-aggregation. So yeah, so I'm just thinking, what is the IPv6 advantage in SSC 3, right? So
I think, yeah, that's a very good question.
yeah,
I'm
very good
thinking
question, but I'm not able to connect to IPv6 though, unfortunately. Yeah.
Yeah, no, I think he's thinking with IPv6 mobility. But I tell you, I know exactly. I think I know what you're thinking too. I have a lot of questions myself about the actual, because IPv6 mobility, that whole stuff about home agent, this, that, and the other thing, that was very pushed at the beginning. I myself am not completely convinced about how much actual implementation there is of that. So I think the thought is that and so I don't know if that's hype or not about seamless address change. You know what I'm saying, Uma?
Oh, okay. Now I got it. Okay. Now I see. Now there's a lot of work that happened in IETF, for example, in DMM working group or mobile IP working group, or or in some cases Lisp. Myself with Dino, we have put proposals. There is a great advantage if you use IPv6 for mobility session continuity in general. But the question was SSC mode 3. SSC mode 3 is defined with 3GPP. So that is using their architecture, that is with the GTP, right? So then the advantage is limited with IPv6. But if you have a clean slate architecture like Lisp for mobility, SSC mode 3 kind of thing, similar functionality with Lisp, that's a great advantage, mobile IP. But the problem with that is it's not a legacy greenfield network, right? It's a greenfield architecture we're talking about. But 3GPP is built over 25 years from 2G to 3G to 4G. Its specifications not much change, the core of the specification, right? So if you put any new mobility architectures with mobile IP and Lisp, it's a huge lift actually. And I doubt it that, that 3GPP will accept it because there's so much legacy there. So yes, though there are technical benefits, it's a backward compatibility issue there.
That's so interesting. So you know what? There's so many questions. I'm going to tell you something. I have a word for that. It's first mover disadvantage. Is that a lot of people, a lot of enterprises, we came early to the game. Started computerizing in the early 70s. Now we stuck. And so yeah, I totally hear you about it's not just brownfield, it's blackfield implementation.
Yes. Yeah. So I think architecture-wise, it's much more harder lift. Putting some of the new concepts into the 3GPP architecture is much more harder. Yeah.
Yeah, and I'll have to talk to Dino too. I mean, as I said, there's so many things I want to do, and as I said, we're running so out of time. And then get one more question, and so because I want to talk to you about about maybe doing a lab demo. We've got some very, very bright young students who can help, and we'd love to see packet traces, in this area, and start talking to some of the people who've done some of this. But I'm going to ask you one final question. And guys, I will try and answer some. I'll send some of these other questions over to, send me the question on email, and we'll see if we can answer those questions via email. And so, because one last question is, carriers like Comcast are pushing V6. Because massive streaming services like NBC Peacock and stuff like that. So what is your, because I think that's very 5G related also. What is your thought? What do you think? Like streaming, 5G, and business, what is the intersection there?
Streaming 5G. The Comcast is big time in their fixed networks IPv6, right? So, what exactly is the question? Streaming related? So can you repeat the question with the streaming part? What is that you said?
Yeah. So whether V6 as a business model is driven by massive streaming services, is V6 better for streaming?
Okay,
I'm not sure. What?
Yeah. So I think if you have all IPv6 networks, there's a lot of legacy middle boxes will be in the path, which can cause a lot of latencies, right? That's the OTT guys' advantage, right? So they control both sides, both the browser side and the infrastructure side. So they can put both side control, and they push the stuff with IPv6. So just to get some performance benefit, latency benefits, anytime you have a legacy IPv4, you have some middle boxes, some firewalls, some NATs, which don't do the right job and introduce latency, right? So these kind of benefits, you have indirect benefits, not directly because of IPv6. It's not that way, but indirectly you get benefited. I'm not sure I answered the question fully specific to that streaming service, but in general I answered, yeah.
No, I know exactly what you're saying. I'm not sure about streaming and because even if you use IPv6 multicast, somebody was suggesting multicast. You know what? I tell you something. I think we really need. There's so many topics that have come as a result of your discussion. There's just it's just so many ideas and so many new things happening. But Uma, thank you so much for coming. And as I say, I'd love to keep the conversation going and start, getting you to talk and some of the other folks you're working with, and then involve you in some of the conversations we're having with the IoT people, Pascal, Karsten, and all those, because they're going to be doing a lot of things. And one final thing, which I'll end with, I know a lot of us are talking also about the power usage and climate change impacts of all this. I don't know. This is such a crazy time.
Absolutely, yeah. Hope this is useful for some of you at least, and happy to connect offline for any questions, other questions and comments. Please feel free to drop a note if you have a specific question. Wherever I can answer, try to answer. Yeah.
Thank you so much. And guys, email me and then I'll bring Uma in to answer. Thank you again. And we'll see you guys.
Thank you, Uma. That was great.
Thank you.
Bye.